Okay, this one's a fairly quick and easy little problem to do, but I wanted to talk mainly for this one about how we set up a problem in physics. These are some good habits to get your students to be doing as they're setting up and working into problems. So the first thing is diagrams as big and clear as possible. I'll be slightly hypocritical about it in this case because I'm working on a little bit of limited space on my tablet, but really I tend to say to students, in learning physics there's no such thing as wasted paper, because if you try and draw a tiny postage stamp diagram, you're going to end up confusing yourself and doing worse at physics. So it's worth taking the time and space to draw a decent sized diagram. So in this case, we've got our little chappy on the roof of a building with an unfeasibly long arm, or I don't know, a selfie stick maybe. He's going to throw the ball downward at an initial velocity of 0.8 meters per second. Sorry, that's a bit messy. 0.8 meters per second. So that's the first piece. We've actually also chosen downward as our positive direction by giving that a positive number. We've chosen that downward is positive. So that also means that the acceleration due to gravity is downward. And we've also been told that it's going to take... So the first piece is draw the diagram. Make it clear, make it obvious what's going on. The second bit is to summarize what we know and what we want to know. So we know that u, the initial velocity, is 0.8 meters per second. We know we're asked for v, the final velocity, and we don't know it. So the final velocity we're asked for. We know that the acceleration due to gravity, a, is going to be 9.8 meters per second squared. And I mentioned that that number is also positive because it's in the same direction as the initial velocity. We could have decided that upward was our positive direction and both those numbers would have been negative. But for this particular problem, it was more convenient. Remember that motion is relative, so it doesn't particularly matter which direction we choose as long as we're consistent about it. And what other piece of info have we been told? We've been told that t, the time from when it gets out of his hand to just before it hits the ground, because once it hits the ground it might bounce, it might sink into the surface, it might shatter. We don't really know what's going to happen, but just a fraction before it hits the ground. It took 0.32 seconds to get there, and we want to know how fast it's going. So let's think about the physics of the problem. It started heading downward at 0.8 meters per second. It's going to be going faster than that because it's also accelerating due to gravity. So it's not going to fall at constant velocity. It's going to accelerate. So we expect that it will be something higher than that. We're not quite sure precisely what it will be. So we've got a number of equations we could use, equations of motion that we've learned. V squared equals u squared plus 2as is one of those. S equals ut plus a half at squared, and v equals u plus at. So the students should have those at their disposal. There could be a formula sheet as well, and we'll have a formula sheet for our course that you can use as a ready reference, but those ones you'll probably use them so often in experiments and experiences that they just get memorized anyway, even if you don't really try to memorize them. But so once you've got your formula, you can say, all right, which of the bits do we have? Do we have an S? No, we don't. So neither of the ones that include an S are going to be very useful to us. We have a V in the sense that we want to know what V is, and we have a U, an A, and a T. So the logical one to use is going to be V equals U plus AT. Now, quite often we have to rearrange the equation to make the thing that we want the subject. In this case, we're lucky because the thing we want, which is V, is already the subject. So there's no rearrangement required. When there is rearrangement required, if we wanted t as the subject, for example, we would have to do some algebra and subtract u from both sides and divide both sides by a. There's a couple of ways of doing it. Some people prefer to substitute in all the values they've got and work with mostly numbers. Other people prefer to leave it and work with mostly pronumerals. Either approach will work, but be flexible. Recognize that your students will have different preferences around these. But in this case, we don't need any rearranging, so we can actually just substitute the values in because we already have what we want as the subject. So U 0.8 meters per second. Again, a lot of teachers will get the students to write all the units in. There are some benefits in that, which is that the students understand units, they memorize the units, they know the units well, they know how they cancel and so on. So maybe we'll do it this time. But my personal preference is to not do it every time because it gets incredibly cumbersome. When you have long multi-line calculations, it can get quite annoying. So 0.8 meters per second equals A times T. So 9.8 meters per second squared times 0.0, sorry, the machine's trying to help me, 0.32 second. All right, and you can see that actual second times second to the minus 2 is going to cancel and giving you second to the minus 1. So the units are consistent. This is meters per second. This overall becomes meters per second as well. And so our overall answer is going to be in terms of meters per second. So that's the benefit of including the units in the calculation, is that you can do that and check that your units are consistent. So in this case, that's going to end up adding up to, let me just double check the answer for reasons that will be obvious to a few people who got in early. So that's going to be 0.8, you can see at the bottom of the screen there, 0.8 plus 3.14, which looks awfully like pi, but that's really just coincidence. 3.14 is 3.94 meters per second overall. Right, so is going to be 0.8 meters per second plus 3.14 meters per second, the units are consistent, equals 3.94 meters per second. And that makes sense because it's a velocity that we're looking for. Right, so that's a relatively long time to go through a relatively short equation, but hopefully what I've also been doing is pointing out a few of the issues that we want to deal with students. And hopefully what I've also been showing is that there are legitimate differences of approach. There's not a one true way to correctly do it, but there are things that tend to be very helpful and things that you might use sometimes and not other times and so on. So I hope that's a helpful example.